In this talk, I'm going to go over a couple of important aspects of probability. Not so much probability theory, just how we should be thinking about probability as it relates to inferential statistics in general. And I'm going to link these into the central limit theorem. The central limit theorem is the cornerstone of everything that we do in inferential statistics. And so it's really important that everybody who takes a stats course has a good idea of what this entails. Here what we see is the normal curve. This is a figure that I took from the Welkowitz textbook at page 94. And so if you have that textbook, you can read up on the text at that point to accompany what I'm saying here. And it's important to know that many real-world examples of variables that occur naturally, they tend to conform to the shape of the normal curve. Not always, but things like height, weight, IQ, things that are more heavily tested in our human endeavors, these are things that tend to conform to the normal curve. And you can see the bell shape of the curve here. Now, a couple of things to point out here. The Greek letter mu, that's this right here. Greek letter mu, that stands for the population mean. Often we don't know what the population mean is. You also see the number 0. Excuse me. You also see the number 0 here, and this is the equivalent of a z-score. 0 and positive 1, positive 2, negative 1, negative 2. The thing to understand here is that when we deal with the normal curve, the standard deviations of the curve, and I'm assuming that you understand standard deviations and z-scores before coming to this video, but the standard deviations of the normal curve are expressed in z-scores. So this is one z-score above the mean, this is two z-scores above the mean, one z-score below the mean, etc. And the mean is 0 because it's 0 z-scores from the mean. A z-score is one standard deviation. So what we're really talking about here is how many standard deviations away from the center anything is. And so next we can notice the numbers here. These percentages are the areas, the percentage within this zone from 0 to positive 1. We have 34.13% of the observations falling. And when I say observations, what I'm talking about are the recordings of the data, the subjects. We could be talking about thousands or even millions of observations, depending on the variable that's being tested. The frequency of variable x is expressed over here. So the height of the curve represents the frequency of the variable that we're measuring. What the normal curve tells us is that exactly 34.13% of observations will fall between 0 and positive 1 standard deviations. And 13.59% of observations will fall between this position on the normal curve and this one. And then beyond this, in the upper tail, but also in the lower tail because it's a mirror image, you'll have 2.28% of the observations falling. What I mean by that is individual scores, people. So if we were measuring IQ, you would expect that 34.13% of people would fall within this range if you randomly sampled from a given population. And likewise, 34.13% would fall in this range. Now, these are not raw scores, these are z-scores, and typically intelligence tests are set by the creator of the test so that you have a raw score of something such as 100 with a standard deviation of 15. So if you're doing an intelligence test, the population mean could be 100. This would be 115, 130, and this would be 85, and this would be 70. So the numbers here tell you what you can expect at any given location within the curve. If you think of the height of individuals, there are a small number of very very short humans and a small number of very, very tall humans. Those two extremes comprise the tails. And it's not to say that they're in any way deviant. It's just to say that they're, the extremely tall and the extremely short, these are unusual compared to, I guess you could say, the average. And if you look at the space in between -1 and +1, you're looking at, if you just add these numbers together, you're looking at 68.26% of the distribution falls between here and here. So most of us fall within this range, and then a few people fall above and a few people fall below. Take another example. A person with an IQ that is measured to be 70, that would put that individual 2 standard deviations below the mean, where the mean is 100, standard deviation is 15. So the test score of 70 would put the person down here, and you can say that only 2.28% of people score worse than the individual with an IQ tested at 70. And that's an important cutoff, both in terms of legal issues such as competency for execution and capital punishment states, where the law from the Supreme Court is that you have to have an IQ of 70 or above to be considered competent. But also in terms of school psychologists' work, where this is a threshold that's sometimes used for ascertaining whether or not a child has a sufficient deficit that enables the child to be eligible for funds for services. So understanding how this works is very important in a variety of different ways. And it's not just important in terms of concrete examples like that, but also because of what it tells us about how statistics work, how probability works, and how we can make predictions about randomly sampled individuals when we take samples of people. So take a pair of dice, and you can see that if we roll dice many times, the numbers will conform to a normal curve, just like many things that occur naturally do. Don't use these dice. It's a little more complicated. It's a 20-sided die. But if we use a pair of 6-sided dice, it's fairly easy to map out the different combinations, and you can see that I've done it here. There's only one way to get snake eyes. There's only one way to roll a 1 on the first die and a 1 on the second die. This is how we would express the probability, where P stands for probability of this event happening, where the event in question is the independent event of rolling a 1 on the first die and then rolling a 1 on a second die. So let the dice over here represent the first roll, and the dice over here represent the second roll. There's only one way to get this. The 1 and the 1 combine. That's the only way that you can get a 2. There are 36 options. How do we know there are 36? There's 6 outcomes on the first die and 6 outcomes on the second die. So it's 6 times 6 yields the total number of outcomes, and you can see that there are 36 boxes here. So the probability of this happening, rolling snake eyes, is determined by taking the number of times the event can happen divided by the number of possible events, and that gives you 0.0278. If you want to turn that into a percentage, to express it as a percentage instead of a proportion, this right here is a proportion. To turn it into a percentage, just move the decimal point over once and twice, and as a percentage it would be 2.78%. So you only have a 2.78% chance of rolling snake eyes or boxcars, which would be 2 6s. In this slide, I computed the odds of getting a 6. 6 is the most common roll, and the diagonal here or actually 7, I'm sorry. 7 is the most common roll, and this diagonal, you can see what I've done is I've highlighted the different ways in which you can get a 7. There's 6 ways that you can get a 7. You can roll a 6 with the first die, it's this one, and then a 1 with the second die. So that's one option for getting a 7. Now that's different from this one, of getting a 1 on the first die and a 6 on the second die. These are two different events that can happen because we're treating each of these two die as being independent from each other. So a 6 and a 1 is different. It's a different event than a 1 and a 6. So at any rate, we compute the probabilities of each one of these discrete events happening, and if we consider it to be a win if we get a 7, and what we want to do is we want to add together all the different ways that we can get a 7. And there's excuse me, I'm coughing a bit because of an illness. So we have 6 different ways of getting a 7. Each one of these has the same probability of happening. You have one different way in which you can roll a 6 and a 1. You have one different way in which you can roll a 4 and a 3. One different way in which you can roll a 3 and a 4, and so on. So you take all of those independent probabilities, add them together, and that's the total number of ways that you can get a 7. So you have a 16.67% chance, or 1 out of 6 chance of getting a 7. You can do this for any type of a roll, and people who gamble a lot do this quite a bit in order to increase their odds of winning. But it's important to understand that these are independent events that are totally random. You don't know what you're going to get till you get it. Now you can map out the different combinations, which I've done here. I actually did this once with, I rolled dice a couple hundred times to see how well it would fit. That was in the old days before computers, and it fit pretty well. But here all I've done is I've taken the different combinations that are possible. To get a 2, you have to roll a 1 and a 1. There are 2 ways to get a 3, 3 ways to get a 4, etc. And you can see that it conforms to a nice normal curve, equal on each side. The probabilities of different events in terms of gambling, games of chance, these were worked out in some detail by de Mauvrais in his text that was originally published in 1718. The third edition of his text was 378 pages. This is the third edition here. I don't have the actual book. I got this screenshot on the internet. And it detailed many different types of events, such as rolling one die 4 times and obtaining the value of 1 exactly twice. So he laid out some of the initial understanding about probability that would then be used by mathematicians later. His intent seems to have been to increase the odds of winning by people who are playing, placing bets, gambling, and so forth. Here are some aspects of the normal curve that I mapped out. You can get these out of the Welkowitz textbook in the section on the normal curve, or really any stats textbook, undergraduate level. Should have pretty much the same information. First of all, the normal curve is symmetrical and unimodal. It's symmetrical in the sense that it has a mirror image on each side. Each side should look like the other. And one outcome of this is that the mean of the set of scores, the median, and the mode will all have the same values. It's unimodal. There's only one peak. The tails of the curve never touch down. And this shows the theoretical possibility of infinitely high and low values, although in practice we never really see that. How often have you seen a human who is 20 feet tall? I mean, I suppose it's possible because the curve never touches down, but in practice it's not going to happen. The normal curve is a continuous scale of measurement, and even if the scores that created it were discrete numbers, like IQ test scores being 100, 101, 105, etc., the spaces in between will have meaning. And this is because the normal curve is an approximation of the variables as they occur in the real world. So the distances in between the markings on the curve, between the observation markings on the scale that was used to create it, actually have real value. The symbols mu and sigma, these are the population values for the mean. Mu is the population mean and sigma is the population standard deviation, are used because the normal curve approximates the true population parameter for the distribution of scores. So we're assuming that we're working with a population, not a sample. It is always true that the approximate proportions of the distribution falls within the specific bounds of the table, those percentages between the standard deviation marks, the z-score marks, the 34% and so on. When the population is normally distributed, random sampling will likely result in a normal curve for a single sample. This likelihood increases as we increase our sample size. And I do apologize about my voice. I'm not doing so well, but the recording has to go on. And so we put our population value here, Greek letter mu. And the standard deviations here are expressed as z-scores. To say that one individual's score is one standard deviation above the mean is the same as saying that that person has a z-score of 1 in the normal curve, positive 1. Here you have the formula for the population standard deviation. It's the sum of, this symbol means sum. It's capital Greek letter sigma. Sum of x, where x is any individual score. You would do this for everyone in the population, which of course is not really possible with large populations. But we take the sum of x minus mu, the population mean, and square those. This is called a deviation score, so we square these deviation scores. This numerator is known as the sum of squares. Take that value, divide by n, take the square root, and that's the standard deviation of the population. And then the z-score is determined by taking any one individual score for variable x, subtracting the mean from it to tell how far that individual is from the mean, and then divide it by the standard deviation, so that the z-score is an individual score's difference from the mean expressed in standard deviation units. If you're doing IQ testing and you had a person with an IQ score of 115, if the mean is 100 and the standard deviation is 15, that would be 115 minus 100 leaves you with 15. Divided by 15 would give you 1, and that would put the person right here, right at this mark. Now, for that person who has a score of 1, a z-score of 1, because of the properties of the curve itself, we can identify what proportion falls below that individual score. From the bottom of the curve to the midpoint is 50%, and then we have another 34.13% here. So the 50% from the bottom to the midpoint plus 34.13% gives us 84.13% from here down. So that we can say that the person with that particular IQ of 115 scored higher than 84.13% of the population. So here's some important points about the central limit theorem itself. So everything that I've been talking about takes us closer to the central limit theorem. We're not there yet. As the sample size increases, the sampling distribution of the means approaches a normal distribution, even when the parent population is non-normal. In other words, if your parent population is skewed and you start sampling from that, the sampling distribution will become normal, even though the population is not. I'll explain what that means in a minute. the mean of the distributions of sampling means is equal to the population mean across repeated samplings. Also, I'll explain what that means in a minute. That is to say, if you repeatedly sample and take the mean of those means, you'll eventually get the population mean. Next, the standard error is given by this formula. This is the symbol for the population standard error, or we can think of it as the standard deviation of the means, but really it's called the standard error. You take the population standard deviation sigma and divide it by the square root of n, and that gives you the standard error. And that's used to define the probability space that forms the theoretical sampling distribution. So this is what happens visually to sampling means as you increase the sample size. So let's say we start with an original population that looks like this. Whatever it is that we're measuring doesn't matter. And in fact, we don't know what the original population scores are because we don't have access to the whole population. If we sample just one person, there's a 2.28% chance that that one person can come from this zone. There's a 13.59% chance that the one person can come from this zone, and a 34.13% chance that person can come from this area, and so on. So with the sampling strategy, where you're only sampling one person, that person can come from anywhere in here, and it's, you can get some very highly unrepresentative data with a sample that's like that. That's why in real research, I should say in inferential scientific and medical research, they don't do it that way. Now, there's a difference between that type of research and qualitative research. I won't go into that here. I do that in a different video. Qualitative research is for different, it has different aims and different ends. So I don't want to say that, please don't think that I'm saying that that's not real research. It is. But that's research for a different purpose. So in those cases, N of 1 is okay, but you're not trying to generalize to the larger population. If you're trying to generalize, if you're trying to generalize, then you have to have larger samples, because a sample size of 1 gives you a sampling distribution that looks like this. It's exactly the same as the original population, and we don't get any closer to where this is. Usually what we're trying to do when we sample from a distribution, sample from a population, for example, we're trying to get information about that population mean. We're trying to figure out, what is the population mean look like? What does it look like? So if we take one individual, this sampling space does not get us any closer to this. Assume that we don't know what this number is for the population mean. If we get one person, that person can come from anywhere in here, and that doesn't help us narrow down where this likely, it doesn't help us narrow down the likelihood of where this population mean is. If you increase your sample size to 4, what happens is that the sampling distribution, the theoretical sampling distribution, gets a little bit narrower. You can see that the spaces here are a bit narrower. Now, it doesn't really get taller like that. What happened is that the photograph editing software that I used made it do that when I squeezed it. So when I squeezed the range here, it made this go up. It doesn't really do that in real life. But you can see that this is narrower. That's the whole point. This range is narrower, and this is called the theoretical sampling distribution. This represents where we can expect our samples to fall if we're sampling with sample size 4. If we have sample size 10, it gets even narrower. Again, it doesn't really get that tall. That's an artifact. It should be more like that. And with sample size 20, it's like a balloon. When I squeeze this, when I squeeze the graphic, the software editing tool that I had made this go way up. At some point, I'm going to have to go and redo those. So you get the idea. The larger the sample, the narrower this range gets. That's the important part here. And you can think of it also like this. When we create a confidence interval, now I don't really go into detail on confidence intervals in this discussion. I can do that elsewhere. And you can read that in the book. When we create confidence intervals, we can define the space in which we expect any future sample to fall. So each of these is a different sampling strategy. And each different sampling strategy, in terms of the number of people being sampled, produces a different confidence interval over here. So the way that you can think about this is that with a sample size of 2, your sample mean is going to fall within these barriers, these boundaries, the lower boundary and the upper boundary, 95% of the time. With 6 in your sample mean is 95% likely to fall within this range, and you can see that the range gets smaller. With 8 in your sample mean is going to fall within this range, and 12 you get even closer. The whole point here is that the larger the sample that you have, the closer your sample mean will be to the true population mean. And if your purpose is to make a guess or estimate about where this true population mean is, you need to have a larger sample to get a more accurate impression of where this population mean happens to be. Small samples don't do it. Small sample could be way off. Your mean could be all the way down here, it could be all the way up here, it could be anywhere in between. And that's one of the reasons why it's important to have very large samples, although extremely large samples are difficult to get. You can think of it this way too. If you're sampling with a sample size of 2, those 2 people can come from anywhere in here, and the chances are that they're going to come from around this region, but the combination of getting 2 people from down here or 2 people from up here is not that unusual. But as you increase the sample size, it becomes progressively more and more unlikely that you pull all 12 people from up here or all 12 people from down here. This is all about the nature of randomness and all about the nature of the probability of randomly selecting people from one end of the distribution versus the other. With larger samples, it becomes more and more unlikely that you get a very biased sample, but with small samples it can happen fairly easily. Okay, so moving on. Here's some text. I won't read all of that, but you can read it on your own. You can stop the video and read it if you like. What I've done here is I've created a graphic of my own. And when I originally did this a few years ago, it took me, I don't know, about 45 minutes to put this together in Photoshop, where I took all these little X bars, each one of these represents a sample mean, and arranged them in a way that I liked so that you can see the shape of this theoretical sampling distribution. So each one of these is a different sample. And the whole point of this is to show that if we have pardon me, I'm coughing quite a bit. If we have a parent population whose value is unknown, and if we repeatedly sample 26 times, the 26 samples will form its own sampling distribution, and the mean of that sampling distribution will, the center point of the sampling distribution should be roughly equivalent to the true population mean. So we don't even have to know what this is. If we sample enough times, eventually we'll find it. But the other point here is that if you only sample once, that sample could be any one of these different samples. It could be close to the true population mean, or it could be far away from it if you have a small sample. Larger samples are going to be closer in because the confidence interval around the larger sample is going to be a lot narrower. And that's why larger samples are better. They're better at estimating where the true population value is. So normally we don't know where the true population value is, and that's why we're doing the experiment in the first place. That's why we're collecting data. And that's why we're analyzing it, because we want to know something about this unknown true population mean. And just to make things a little bit worse, if this is a 95% confidence interval, that means that 5% of the time we'll get a sample that falls outside of this just by accident. And so we really do accidentally sometimes select people from the high end or the low end too much, too many of them in a sample, and it makes our sample look biased and not fall within this range. So that's always a chance. With any given sample, we don't know how close it is to this true population mean. All that we have to go on is the position of the sample. But if we have multiple samples and we add them together, then we get a better estimate of where the true population mean is, and that is the essence of meta-analysis, where meta-analysis involves the summarizing of data from different independent studies and getting an average effect size across all the studies. If you were able to get 25, 30 different samples using the same methodology, you'd have a pretty good notion of where that population mean is if you aggregated all those samples together, took the average of the means. So the repeated samples themselves will tend to form a normal distribution, and that's true even if the original parent population was not normal. If this is skewed, the repeated sampling down here will form what looks like a normal theoretical sampling distribution. And remember, we call this a theoretical sampling distribution because we never actually repeatedly sample the way that it's shown here. We don't have the resources to do it. If we had a very large sample size, then the confidence interval gets narrower, but even then we're still going to have 5% of the time the sample mean that falls outside. Now here's a screenshot from a program that I'm going to illustrate for you. This is the ESCI program by Jeff Cumming. I admire Cumming's work very much. Highly recommend his book, The New Statistics. And I'm going to use his ESCI program to generate a series of samples. Each one of these green dots represents a different sample, and the sample statistics can be specified over here. This is a screenshot, so I'm going to open the program itself. I've got it open here, and so you can see the program at work. And up here you see this is the parent population that we're drawing samples from, and the population mean is set at 50 with a standard deviation of 10. Actually, let me change that so that it looks more like intelligence test scores. Let me make this 115. If you find his web page online, you can do this yourself. Well, I don't know. Let's see, I guess the scale is changed. Let's see, how does this work? Hang on, let me figure this out and come back. Well, I couldn't quite figure that out to change this to have a curve that represents the population for IQ tests, but I'll just continue with the basic default setup where the mean is 50 and the standard deviation is 20. So one thing to notice is that you can change these things if you want, but it also changes the shape of the parent population curve, and I wanted to keep this up top. Notice over here it's got the n, the sample size is 20. That's a pretty good one to use for testing purposes. And I'm going to tell it to run. Now what we see here, I stopped it, what we see here are blue dots and green dots. The blue dots represent one sample of sample size 20, the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and another 10 over here. You get the idea. Each one of these is an individual data point of sample size 20. So we've got 20 data points represented here. And that brief time that I ran it, this is a random number generator. That brief time that I ran it, we had 3 samples created. And you can see these green dots are going to fall down here, and they're going to make a heap and this represents the theoretical sampling distribution based on what we see being generated up here. So every time you sample, you're going to get a sample either from up here or down here. The width of that interval is going to be based on the confidence interval that's built. If we go back to the PowerPoint, it's this. You know, it's this what we're talking about. This buildup of samples that's defined in terms of the range of possibility that's dictated by the sample size. The larger the sample means you'll have a smaller range in which the samples can appear, whereas larger samples, if you have a larger sample size, this range will be narrower. So what we're playing with here in Jeff Cummings' program ASCII is a fairly small sample, or at least relatively small, of 20 people. You don't really call it a large sample until you get over 100, I think, although there's no firm rule on that. It's different for different applications of stats. So I'm going to run this and let's watch what happens. You see that each one of these samples is being randomly created by the numbers up here. The means are falling down like snowflakes, and they're starting to build up at the bottom. Notice that the center of gravity at the bottom appears to be the number 50, which is the true population mean up here, set when we started the use of the program. And you can see that these sample means are very slowly but surely building up in what appears to be a normal curve. You don't see means all the way up here. You don't see means all the way down here, because it's statistically incredibly improbable that you can randomly select all people from the top side or all 20 people from the bottom side of the population curve. So if you know nothing else about what the central limit theorem is doing, this is really one of the most important things. What the central limit theorem is doing is it's dictating, based on the sample size, the range in which any future sample can fall. And one of the points in the central limit theorem, one of those three things, was that the mean of the means will equal the population mean. So I just stopped it here. If we took all of these samples, and right now we've got, let's see, it should say here how many samples we have somewhere, 242 samples. We've done 242 samples, which is quite a lot. If we take the mean of all of these means, it should equal about 50. Now these are not all possible, theoretically possible means. That would be impossible. But you get the idea that the more samples you have, if you take the mean of all of those means, the more likely those means will equal to the original population mean. But what we do see is a nice normal shape here. And let's see, I think we can, yeah, right there. So I click the button for the sampling distribution curve, and you can see that it's nice and normal underneath that after smoothing it out a bit. And so the basic principle of the central limit theorem has been upheld by this random number generator in a nice way. Okay, so going back to the PowerPoint, so this is one that I did some time ago using an older version of the software, and you can see essentially the same thing, although the one that I just created was nicer in appearance. But here's the point. The mean of the means equals the true population mean. The mean of all of these means, if you do every possible sample mean that you could theoretically do, if you were doing, let's say, sample size of 10, how many different samples can you draw from 1 million people of sample size 10? With replacement, putting them back and sampling again and again and again and again and again and again. I mean, it would be an incredible number of samples. Too many to ever do. But if you took the mean of all of those means, it will equal the original population mean. I tested that out once with a small number of small size population, and in fact it did work. I was just curious and I guess bored one day. That was about, I don't know, 10 or 15 years ago. And it did work. It gave me the population of the original, it gave me the population mean of the original population when I took the mean of all possible sample means. I have that in my notes somewhere. I should bring it out someday. Yeah, so that's I won't go into this. This is a graphic from one of Jeff Cummings' articles. It's interesting by itself. But I guess let me say this one thing about this graphic here. Using the random number generator, what you see based on any given sample size and standard deviation, here we have sample size of 32 with a standard deviation of 20, and that part we don't need to attend to, just focusing on this sample size 30 sample size of 32 and standard deviation of 20. If this were a real experiment, these would be all the different possible outcomes that we can get on 25 different replications, and he did this using his random number generator. Some of them are significant, some of them are not. And so that's a real problem when it comes to experimental research in psychology and other fields, that oftentimes when we have an experimental result that's significant, we don't know if it's just blind luck or if it really reflects some inherent quality of the treatment effect. And we need to recognize that the sample means can bounce around quite a lot, and this is all random. It's just random factors. So it's one of the key elements of the central limit theorem. So to excuse me. To summarize, going back to our 3 points of the central limit theorem, the most important of these is the standard error. And the standard error is in turn used to create the confidence interval around the sample mean to give you the possible range in which you can have the population value. So if we have, let me go to one of these. Let's say we have a sample mean that's out here. If we had a sample mean right here, right where the cursor is, we would take this interval and place it around the, I should have a graphic for this, but I don't. Place it around where the cursor is, and that would be the confidence interval in the around the sample that we collected. And the reason why this is so critically important is because the larger the sample, if your sample size goes here, the smaller this gets. If you sampled sample size of 1, the standard deviation, the population standard deviation divided by 1 equals the same thing. So if your population standard deviation is 10 and your sample size is 1, then the standard error is still going to be 10. It doesn't change. So again, if your population standard deviation is 10 and your sample size is 1, then the square root of 1 is 1, and 1 divided into 10 gives you 10. So this will not change. But let's say you have a population standard deviation of 10, and let's say you're sampling with sample size of 200. That would be considered a large sample. The square root of 200 is 14.14, and then when you take that 14.14 and divide it into 10, you get an outcome that's 0.70, actually 0.707, so it's called 0.71. And that is a lot smaller. The larger the sample, the smaller this number gets, and that is very useful in terms of narrowing the confidence interval that makes our estimates of where the population mean is much more accurate. So that's really the key thing. Okay, so I hope this was helpful, and I hope my coughing hasn't been too tiresome to listen to. Hopefully I'll feel better by the time I do my next video lecture.